All right, 10.1c, significance tests for difference of proportions. So researchers designed a survey to compare the proportions of children who come to school without eating breakfast in 2 low-income elementary schools. A simple random sample of 80 students from school 1 found that 19 had not eaten breakfast. And then at the other school, a simple random sample of 150 students included 26 who had not had breakfast. More than 1,500 students attend each school. So do these data give convincing evidence of a difference in the population proportions? So, first they're going to have us state the hypothesis. So we are going to do the 4-step process. They do the first part for us. So we're going to state. So our null hypothesis is that the difference is 0. So there's no difference. And the alternate hypothesis is that P1 minus P2 does not equal 0. This means we have a 2-tailed test, and we're going to double our answer at the end. And then be sure you define your parameters. So P1 is the true proportion of students at school 1 who did not eat breakfast, and P2 is the true proportion of students at school 2 who did not eat breakfast. All right, so this would be under the plan step, where we need to check these 3 things. Just like the confidence interval, same thing as before. So, random, got to have a random sample, and both of them have to be random samples. And then we need our 10% rule. Notice we're checking both. And large counts, n times p, n times 1 minus p, and same with the other one, so check both. And they have to both be at least 10. And then when we find our test statistic, we're going to do the same formula. Our statistic minus the parameter divided by the standard deviation of the statistic. Our standard deviation is going to be different. So, this is the one that we did for confidence intervals. And so for confidence intervals, you use separate proportions. So notice we have our p hats, we have P1 and P2. So for this problem, P1 with the hat on it is 19 out of 80. And P2 with the hat on it is 26 out of 150. And we would use separate. However, we're not going to use P hat 1 and P hat 2. We use what's called P hat combined, or sometimes they use the word pooled. So we're going to pool them together into one fraction. So we're going to add our numerators together. So we're going to do 19 plus 26, so everybody who has not eaten breakfast, divided by the total of both schools, so 80 plus 150. This gives me 45 over 230, which is 0.1957. So the formula that you want to write down is PC with a hat on it times 1 minus PC plus PC times 1 minus PC. So you're going to use the same number in all of these spots, but we are going to keep our separate ends, and our ends are the 80 and the 150 for this problem. So let's go back and actually do the plan part of this. So we've got our state, and now we've got our plan. So the test name, which you definitely want to write down, this is called a 2-sample Z test for difference of proportions, or P1 minus P2. So remember, it's 2-sample because we have 2 proportions, and Z's always go with proportions. All right? And then we're checking, is it random? And yes, we had independent random samples. For both. 10% rule on both of these. So we need to check that we've got 10 times 80. So this would be at least 800 students at school 1. Okay. And then we've got to have at least 10 times 150. So we need at least 1,500 students at school 2. So what does the problem say? More than 1,500 students attend each school. So we're good to go with the 10% rule. Then we need to check large counts, n times p. So I've got 80, which is my n at the first school, times 19 over 80. And then 80 times 1 minus this is 61 over 80. Notice the 80s cancel, and the 80s cancel. And then at the other school, we have 150 students, and our people who didn't eat breakfast was 26 out of 150. Notice that the 150s cancel. And then we have 150, and 1 minus this would be 124 over 150, which gives me 124. And so are all of these greater than or equal to 10? Yep, this one is, this one is, this one is, this one. So we're good to go. We have large counts, which means we have normality. All right, so we've got our 2 different p hats. So 19 out of 80 and our decimal, 26 out of 150 and our decimal. And we want to calculate a z-score. Well, first we need the difference between p1 and p2, our hats. So 0.2375 minus 0.1733 is 0.0642. And we also need to calculate PC, which we did 19 plus 26. So this is our pooled statistic for the standard deviation, 0.1957. So we always do the statistic minus the parameter divided by the standard deviation. So the statistic would be the difference that we calculated. And the parameter is what the null hypothesis is. We would expect it to be 0. And we're going to divide by our formula for standard deviation, which now we're using the pooled number, 0.1957 times 1 minus 0.1957 divided by n1, which is 80, plus same number, 0.1957, 1 minus 0.1957, and this time divided by 150. So this gives me a z-score or a test statistic of 1.17. Now remember, this is two-tailed, so when you draw your normal curve, not very straight, but there you go. 1.17 going this way, negative 1.17 going this way, okay? So p-value is the area under the curve, and we use normal CDF. Remember to label. So our lower bound, I'm just going to do the right tail. So from positive 1.17 up to 10,000 or 1,000. And our mean is 0 because we standardized it, and our theta is 1. And we get 0.121. Remember, that's the area right here. So I need to double it to get my p-value because it is two-tailed. 0.242. So the area under the curve here is about 24%. All right, so we're checking, is that smaller than alpha? And for this one, we were using the 5% level. So is the p-value smaller than 5%? Nope. So because our p-value is 0.242, which is greater than alpha, we fail to reject the null. There is not convincing evidence that the true proportion of students at the 2 schools who didn't eat breakfast are different. All right, so how do we do this on the calculator? So go ahead and write this down. Menu, statistics, stat test, and it's 2 proportion z-tests. So remember, we were doing proportions and z's. For this guy right here, 2 sample z-test. So if there's a z, That doesn't always mean proportions. It doesn't say proportions. This one is for means when we know the population standard deviation, right? All right, so let's try this one on the calculator. So go to Menu, Statistics, and Stat Tests, since we were doing significance tests. And again, look for proportions, and it's 2 proportion because we have 2 p's. And we're going to plug in x1. So this is never a decimal. This is going to be 19 out of 80 students who didn't have breakfast at the first school, and the other one is 26 out of 150 at the other school that didn't have breakfast. And we're looking for a difference. So P1 does not equal P2. And check and make sure we got all of that right. So 1.17, p-value of 2.242, and this gives me p hat 1, p hat 2, okay, and 1 and 2. And this is our p pooled. So everything we need. All right. So another important thing to note, inference for experiments. Most experiments on people use recruited volunteers as subjects. So when subjects are not randomly selected, researchers cannot generalize the results of the experiment to some larger population of interest. It can only be generalized to people like those in the study. Okay, we can draw cause and effect, but again, only to people like the people in the study. Also note that unless the experimental units are randomly selected, we don't need to check the 10% condition when performing inference about an experiment. Okay, so look and see if they're randomly selected. All right, cholesterol and heart attacks. So high levels of cholesterol in the blood are associated with higher risks of heart attacks. Will using a drug to lower blood cholesterol reduce heart attacks? The Helsinki Heart Study recruited middle-aged men with high cholesterol but no history of other serious medical problems to investigate this question. So notice they recruited them, so they did not necessarily have random selection. They did do random assignment right here. So the volunteer subjects were assigned at random to one of 2 treatments. So 2,051 men took the drug gemfibrozil to reduce their cholesterol levels. And a control group of 2,030 men took the placebo. During the next 5 years, 56 men in the gemfibrozil group and 84 men in the placebo group had heart attacks. Is this difference statistically significant at the 1% level? So we're going to state what we're going to find. We hope to show that the drug gemfibrozil reduces heart attacks. So we're going to have a one-sided alternate hypothesis. All right. So for the null hypothesis, we want to know, or we would assume the null hypothesis, that there is no difference. All right, and the alternate would say P1 minus P2 is less than 0. You could also write this as P1 is less than P2. And you can also write this one up here as P1 equals P2. So they're the same, or we're going to have less people who took the drug in the first group that had heart attacks. And of course, define your P1 and your P2. So these people took the drug, and the second group took the placebo. And of course, you got to state your significance level in the state part. All right, for the plan, we're going to say what kind of test this is. And we're going to check random and large counts for this one. So for our test, we've got the same thing as before. So 2-sample z-test for difference of proportions. All right, and do we have a random sample? Yep. 2 groups in a randomized experiment. And then because of this right here, so note, unless the experimental units are randomly selected, we don't need to check the 10% condition. So we did not randomly select our people, so we don't need to check the 10% condition. However, we do need to check for large counts. We can kind of take a shortcut here, because if I multiply the number times the fraction we're looking for example, we have 2051, and then how many of those 2051 had heart attacks? We had 56 out of 2051. And just like before, these are going to cancel. And we get 56. And so the other number we're looking for is just this 2051 minus 56 for large counts, which is 1,995. Okay, and then the other one, we had 84 out of 2030. So we've got 84. And then 2030 minus 84 is 1946. So you don't necessarily have to show this, but we do need to list that every single one of these is greater than or equal to 10. And so we have large counts. All right, so we need to find p hat 1, p hat 2, our pooled p hat, our z-score, and our p-value. So let's do this all on the calculator. So we go to menu. And you guys should be doing this with me. Statistics, stat tests, two proportion z-test. And for this first one, we had 56 in the gemfibrozil group out of 2051. And for the second one, we had 84 who had a heart attack in the placebo group out of 2030. And we are looking for less heart attacks in the first group than the second group. So our z-score is negative 2.47. We do need to write that down. Okay, p-value is one-sided, so if we did do normal CDF, we would not multiply by 2. So 0.007. And let's see if they give us all the p's that we need. P hat 1, 0.027. P hat 2, 0.041. And the combined 0.034. All right, again, don't forget how to find this. I will put this on the test. So use your formula. And then we want to look at our p-value and compare it to our alpha. So for this one, we're looking at the 1% level. So is this p-score less than that? Yes, it is. So because the p-value 0.0068 is less than 1%, we can reject the null. So the results are statistically significant at the 1% level, and there is convincing evidence of a lower heart attack rate for middle-aged men like the ones in the study who take gemfibrozil than for those who only take a placebo. So how come we can only say like the people in the study who take gemfibrozil? Because we didn't have random selection, we had people who volunteered for the study.